New brain implant begins human trials. Elon Musk's Neuralink brain implant firm is the billionaire entrepreneur's foray into the experimental medical market known as brain-computer interface, and enormous progress has been made in the 6 years since Neuralink's inception. Some of it comes from Neuralink's work implanting gadgets into pigs and monkeys, including a now-famed monkey that can play Pong with only his thoughts. Because of the digital telepathy offered by brain-computer interface technology, the next generation of brain-computer interfaces is now undergoing human testing in the United States for the first time. However, the first brain-computer interface operation to be authorized by the FDA will be a system called the stentrode from a rival private business called Synchron, not a Neuralink. Knowing our regular audience, some of you may find this news disturbing. But let me quickly turn this around and add that this is a fantastic thing for everyone. Since competition is the greatest way to move an industry ahead, Neuralink and Elon Musk were included. Strong market competition and a diverse range of products will stimulate innovation and new discoveries. So, let's look to the current situation of the brain-computer interface sector and how Neuralink fits into it. So, when Neuralink was initiated in 2016, there was a lot of hype and press attention around the firm, and it was solely due to the project's creator, Elon Musk. The news was filled with reports of Elon Musk putting implants in human minds that would heal all ailments, make you wiser, allow you to manage a computer with your brain, and even connect with an AI technology to transform into a human-machine hybrid super creature. It was all a little out of this place, but that's how things go with Elon. He has no censor, so he simply says whatever wild fantasy ideas are in his head, and the media repeats it. So, while Elon Musk did not develop the brain-computer interface, it has been around for a long time. The only issue is that there has been essentially no development in refining the approach and execution of the brain-computer interface between 2016 and the mid-1990s. So Neuralink comes into play. It's a fresh take on an old technology that does exactly what Tesla achieved for the automobile market. They did not develop the electric automobile, but they did pack that innovation into a vehicle that performs well and solved an issue inherent in the initial design. The brain-computer interface idea is rather basic. Your brain is really just a mushy ball of electric flesh that controls the rest of your body by creating precise electrical impulses and sending them out via your nerves and then into your muscles and organs. Those electromagnetic pulses are analogous to the human body's programming language. Your brain sends commands through your spinal cord, but this link between the brain and body might be severed by a physical injury or a degenerative illness. As a result, the brain-computer interface can act as a bridge for those electrical impulses, allowing them to escape the existing brain-computer interface's broken link. Existing brain-computer interface technology may be classified into two types, invasive and non-invasive. You've most likely seen non-invasive brain-computer interfaces. It looks like a strange headgear with a slew of electrode sensors across it. This can interpret electrical impulses from the brain, although it's not very good at it. It's hardly surprising that it's ineffective because there's a full skull between the sensors and the neurons. It's like attempting to listen to a song from the stands. You may hear the thuds and the bass notes, but not the vocals. Thus, to make a proper connection to the brain, we must be intrusive with our brain-computer interface, and here is where things become unpleasant. The Utah array is now the industry norm for invasive brain-computer interfaces. It's a square computer chip with a number of spikes emerging from it. I'll give you a hint, those spikes are heading into your brain. So they take a part of your skull and chop it out. The Utah array is spiked into the outermost layer of your brain, and then a tiny computer device with a huge wire going out the other end is attached directly to the top of your skull. Typically, they will have to repeat the process twice. As a result, you'd have two spikes in your brain plus two computer boxes with cables protruding from the top of your skull. It's rough but it works. The spikes can swiftly and readily receive electrical signals from the brain's cortical area, which are then scanned by the computer and converted into computer code, allowing a person with a brain implant to operate an electronic device with their brain. They can use a robotic limb as if it were their own arm, or they may manage a computer to relocate a mouse or type on a keyboard. The disadvantage of this procedure is that it can only be used once. Individuals can't go around their lives in medical research context with all of this material spilling out of their skulls. They can't even do it at home since the Utah array is basically a collection of little nails on the surface of your brain. The body will seek to reject the invading thing. It will get irritated and produce scar tissue around the puncture, rendering the device ineffective. So we've arrived at the next generation of brain-computer interface technology, which firms like Neuralink and Synchron are leading. As previously stated, Synchron is the first to enter complete human testing. They started testing in Australia with 4 individuals receiving their brain-computer interface implant. According to reports, Australia has lower laws around what may be placed into a person's brain, while the FDA just last year approved Synchron to begin human testing in the United States. The first patient in the United States has just had their stentrode implant and will be the first of 6 individuals engaged in the $10 million trial. The National Institutes of Health supported a study to determine why Synchron passed the barrier before Neuralink. We can examine their implant's design. The stentrode takes its name from a popular medical device known as a stent. This is nothing more than a long, thin, flexible tube that doctors may place into a patient's blood artery. Stents are frequently utilized in various operations, the majority of which involve the heart. If the artery is clogged or constricted, your doctor will install a stent tube to keep it open so the blood can circulate and you don't suffer a heart attack. So the stentrode is exactly what it sounds like, a stent attached to a cluster of electrodes. The Synchron treatment involves inserting the stent into the patient's jugular vein using a catheter and running it all the way up into a blood artery nestled inside the brain's motor cortex. When they draw back the catheter tube, the stentrode hollow wire mesh expands out and interfaces with the blood vessel walls. The wire at the opposite end of the stentrode is attached to a tiny computer device implanted inside the patient's chest cavity. If this sounds familiar, it's because it's almost exactly the same technique as implanting a pacemaker. They're just inserting the cable into the brain rather than the heart. The implanted device will then link to the rest of the system through Bluetooth, which may be paired to either a computer or a smartphone. The benefit of the Synchron operation is that nothing will protrude from the individual, and there will be no apparent indication that they have an implant in their brain. The system may be utilized anywhere. The procedure may be performed in any medical environment in a matter of hours, and there is no need to open the patient's skull or harm their brain tissue. The first patient in America to receive a stentrode is a person with ALS who cannot move or even talk. This individual may now use a computer and interact by text simply by thinking, owing to Synchron's gadget. The sole disadvantage to the Synchron is that it only exists within a blood channel that travels through the brain. The electrode is not physically engaging with the neurons since it is not embedded in the cortical tissue. So, because the signal entering via the stent route is restricted, it cannot match the bandwidth of the Utah array. Synchron is unquestionably solving many difficulties. What do you think of this new brain implant in humans? Is it worth the risk? Comment below. If you enjoy the video, make sure to like, share, and subscribe. Thanks for watching.